Okay, so welcome back, everyone. So let's see. This has been a wonderful set of talks. I really learned a lot. I hope you did too. So this last session is meant to be a discussion session with several of the speakers and Nati, who from the audience managed to give a talk as well. So we included him too. And actually, the discussion also includes everybody. So, we'll start with the people on the stage in terms of speaking, but everybody should feel free to chime in with either answers or questions or points of discussion. So, maybe I'll try to sort of say what I'm hoping that the discussion will include, but it should be anything you want it to be, anything you want it to be too, among the speakers. But one of the purposes of this bootcamp was not just to get everybody up to speed on the background, but also to help point us all in good directions for this semester, the LLM semester. And so I was hoping that this discussion would lead us to, it would be a way to jointly discuss what might be, the ambitious but achievable projects that we could work on. What are questions that are unsolved, but that maybe outside of this setting people wouldn't be thinking about tackling them possibly, but here, given that we have people from so many different areas converged, and as Surya said, where we might be actually kind to each other and interact with each other. Well, what could this lead to, and what would be sort of ambitious but not impossible? What are those kinds of questions that we might be able to tackle? So that would be one thing. Maybe along the lines of the kindness, another thing maybe to discuss would be, what are modes of research we could imagine, which would get us outside of our comfort zones and really talking to each other. What are these possible ways that we could be thinking about questions? And then finally, one other thing that I wanted hopefully to touch on, if somebody is interested, is I think there are almost everybody is here from academia, some with industry hats, but still, starting from academia. And so I guess there's a real question to what extent, what kind of research on LLMs is possible outside of industry? To what extent can we actually, we can ask people from industry, where do you think we'll be in so many years, or where are things going? But it's also interesting to understand what that view is from academia, from looking in from outside, or what's possible to do out here. And of course, there's also the question, we do plan to engage with industry over this semester and the year. And so what would be fruitful ways of doing that in the context of still this question, what are ambitious but feasible projects that we might work on? So I'll turn the floor over to you, and in any order. But if people don't don't jump in, then we could go this way across.
I'll jump in because I see what's coming. Yeah, I think. It's not on. Oh, sorry. Yeah, I think a lot of the things I said in my talk a couple of days ago as good directions, I think are still good directions. I think we've been hit over the head with these amazing capabilities, but it's going to be hard to understand them in uncontrolled data sets like the entire internet so I think we need to go back to controlled mathematical models of data and obtain a much deeper understanding of in what sense are they creative on data sets, when can they do out of distribution generalization, when can they not, how can we make the training more efficient, what do they actually learn. I think this question of creativity is one of the biggest questions of our day. Like, are they really creative? Like, it's actually very hard to tell whether the frontier models are creative because we don't know their training set. Without knowing their training set, we can't answer that question. We just heard about the possibility of data contamination and evidence for it on benchmarks. So we need to go back to open source models where we understand the data and we try to ask that question there. I'm quite excited about like our recent theory on combinatorial creativity and diffusion models, where it combines the training points in understandable ways to create new test points, new samples. I think that can be pushed further into semantic domains and things like that. Yeah, those would be some things that I think are interesting directions.
Yeah, I'm not. So I think we heard lots of really interesting. I completely agree. We heard lots of interesting directions and in many talks. And I also, as somebody in the audience, I have to say that I was very felt happy that in many of the talks there were questions, either theoretical questions or questions really that I think at least can be formalized as theoretical questions, or even better than that, questions where I almost, there was like, okay, there's a theory that exactly like fits there, which really can help, I think, explain. I think this was, today in Yejin's talk, and there's a lot of that in Roger's talk and in Danqi's talk, but there's all over the place.
Actually, if you would take a few minutes to enumerate the ones that really stick out in your mind, or
okay, I feel a bit. Yeah, I have
or
to
maybe
say,
a couple of them.
I didn't prepare. I was asked to be here full like 2 minutes ago, and I didn't prepare. So I feel a bit like I don't want to, not.
But this is a big question that you and suddenly you're supposed to deliver.
Well, this way you don't.
So I can. Okay. So maybe because Roger isn't here, I'll maybe mention. I think Danqi and Yejin can talk for themselves, but I'll mention some of the two of the questions that I took away from Roger's talk, if I can remember them. So one of them is how does the pre-training change the? So this is my take on it. How does the pre-training change the computational complexity, or the what I would call the dynamic complexity, the runtime of SGD required to learn certain functions? So this is my like hyper theoretical take on this. We have functions that, in terms of the post-training data, I have enough data to learn them, but they're computationally may be very difficult. How does the pre-training data make these problems easier to learn computationally, or with less runtime of SGD, which to me is almost the same thing. And we have lots of understanding, I think, on how does pre-training data make tasks that we learn in post-training easier statistically. That I think we have lots of understanding on. But I think this computational twist in it is maybe something we don't understand as much. And is what I find it nice about this problem is completely approachable. Like, I think it's not like some like these high in the sky problem that we can like NP is equal to NP, that like whatever, we're not going to make progress on this quarter. The other question from there's another question that I'm trying to remember from Roger's talk. Was the generalizing. So generalized to new environments. How does pre-training make it possible to learn well with even with few samples from learn well on specific environments, even with few samples from the environment? So again, Roger, I think, viewed it as a negative thing because he was worried about the safety aspects of this, but the the problem in terms of a learning problem, I think, is basically understanding this ability to learn even with small amounts of data that's not separated out. But like if I have within my training distribution a small nugget, how can I learn just based on that by virtue of the pre-training? So maybe that's not quite as crisply formulated, but I think very close to that. So.
I had some different answers. I got very biased by the context of Nati here. I think the question of characterizing the pre-trained initialization is super interesting. Like especially, I think we weren't able to find even synthetically really simple, clear, convincing cases that optimizing on a set of tasks, like pre-training on a set of tasks, actually allows you to learn a new task like significantly faster. There was some work from CMU, from Zico Coulter's group, that showed how if you look at ImageNet pre-trained initialization, they try to match some, like they saw that the statistics of the weights were a little bit different from random, and they just tried to match that rather than actually training on ImageNet, and they were able to get as much gains in all the downstream tasks that they were seeing. So maybe there's a much simpler explanation for like what are all the gains we're getting from pre-training, and there could be some analysis to do there. And I think there's no nice way that we currently have for analytically thinking about like what is happening with the pre-trained initialization. I guess some other things that I've been interested in is, I think, seeing the kind of, I come a little bit from, like, I did TCS in my undergrad, and I love guarantees and worst case stuff. And I feel like it's been kind of interesting to see our average performance on so many tasks has really gone up. But I can't name one task that models have now solved at 100% that they didn't solve 5 years ago. So I am kind of curious as to like, how do we bridge this gap? Like, should we hope to bridge this gap, or do we need new ways of thinking about like what kind of guarantees, like how do we actually deploy these systems, like what do we expect from practice? And yeah, maybe there's I think we need like a good definition for safety, robustness, even performance. And I think benchmarks served a good substitute for that so far, but as Tatsu alluded to and the conversations there, I feel like now we've basically overtrained on all these benchmarks, and they're not even serving their held out purpose. And we are more ambitious in that we want a general purpose agent and stuff like that. So I feel like we need to really think about how do we define formally good performance that's also reflective of what we actually need from practice.
Okay, I would just say two things I'm currently very interested in. The first thing is the potential of the small models. Like back to 1 year ago, when we start training some like models 1 billion, 2 million sizes, we never thought about these models could be as powerful as like just we are seeing today. So there are definitely a lot of things we can do, like what we can put in post training. So if we really do things correctly, the smaller model still have huge room for improvement. And also what kind of things we can do in pre-training to train these models to become more powerful. This is the first thing. The second thing I'm very interested in are actually some challenge tasks that the current models are not able to do. So right now, the current practice is like we have like collection of the pretty standard benchmarks, and we just keep improving the capacity of the models, and we do very simple prompting and to compare the performance. But there's still a lot of the challenge tasks that they cannot just be solved by simple prompting, by just fitting in a couple examples. For example, like Olympic problems, or like actually, this year, some of my students actually working on something called ARC prize. I don't know if some of you heard of this. So it's very simple, few short examples. But if you just fit in these models, they just cannot solve it. So to solve these really challenge problems, right now, a lot of solutions actually rely on search. So you have to take the models, you put a lot of compute, do a lot of search in the inference time, and then you can get some of the problems can be solved to some extent, but some still not there yet. So another really challenging question to think about is, because people do a lot of hacking things to do the search, to do prompting, to make things work, whether we can move a lot of this compute back to training, and then still use some simpler prompting to make these things work for harder problems.
I agree with a lot of great directions, which also makes it harder for me to add anything new. So I'll make some meta comments. I think in general, engineering, versus science of LLMs is such that really science is lagging behind the engineering breakthrough. So especially from academia, we can really help, engineering oriented efforts in non-academic world by doing more scientifically minded research. And then similarly, I think the performance or capabilities are advancing faster than how we know how to evaluate. So evaluation is lagging behind the capabilities. And, it used to be that you make benchmark by crowdsourcing the data set, and that was that. But the problem with that is that, well, it kind of looks like easy to overfit. And then you don't really trust if it's saturated because there are always other out of distribution examples where the model might fail, which creates new scientific challenge to us, such that I think we need to think about how to discover that unknown or unknown unknowns somehow, either algorithmically or in some inference-based way or some reasoning-based way. And I think there's a lot of potential there. How do we find, how do we find the problems where these models might break? And then there's this question of, I don't have enough compute, then what? So I'm with Danqi, especially about, the emphasis on smaller models. And on that note, I personally think that algorithms are perhaps undervalued in the current climate of let's just do everything end-to-end training because, it feels right. But the truth is, let's remind ourselves that AlphaGo was not just the success of a deep neural network, in that in order to train it successfully, they really had to do imitation learning on the Monte Carlo tree search algorithm's behavior. And then they couldn't get rid of it during test time, inference time. They still had to run it on top of the neural network predictions in order to make sure that it does do better. So neural network alone was not able to close the gap between what algorithm, discrete search basically is capable of. We started seeing some such trend these days where we start thinking about more like, in some sense, compound AI approach. Compound AI, the concept is from Berkeley, by the way, Mate and others. So we build maybe a system that use LLMs as a module, but you might have some other inference algorithm. And in my own experience as well, I was having a lot of fun with either discrete search algorithms or continuous search algorithm, what I would call as continuous search algorithm, which is basically gradient-based search, working together with off-the-shelf neural network. And it's a really fun space that I think is underdeveloped, and that's really great research direction to consider, especially, if you feel like, I know algorithms, I just took, data structure classes, I know these theories, but somehow I don't have a compute, then, algorithm is great. It's more fun than hyperparameter tuning. Lastly, I think there's really a lot of potential impact of LLMs on society. And if you are more like socially minded or humanity, if you have some understanding about, humanities fields, then now is a really good chance to really leverage your unique interdisciplinary potentials, because there's a great opportunities for AI and laws, AI and policy. These are beyond me, to be honest, but I really appreciate people who do push toward those directions, and AI and literature and AI and, philosophy. I think really there are new directions that are about to begin, and you could really be the leaders for those.
I'll probably just say something that are much more theoretically minded, I guess. Maybe on one end of the spectrum, I find it very curious that language models are used in these two different dual roles. One is for prediction, one for generation, yet somehow it's like the same object doing this. And we saw there's sometimes some tension between these two objectives. I find this pretty curious, and don't know why this is somehow always just done with the same architecture. Another thing I think kind of recurs every time I see a panel like this related to machine learning about how do we make further progress in theory, and somehow there's always an answer. I'll just give it now, which is that, well, we don't understand data very well. We don't have good models, theoretical ways of thinking about data. Obviously, it's not Gaussian. It's not uniform on a cube, but it's also not the worst case data. And I think maybe in the context of language, maybe we might have better ideas of tractable models of data, just because it's something we're much more familiar with. So that might be like a fruitful avenue of investigation. Slightly closer to, only slightly closer to practice might be to think about different abstractions of language, transformers and language models that let you use them in different operating modes. Like I know this thing called retrieval augmented generation people have been talking about a lot lately. Maybe this is the model that you could actually theoretically think about just using a language model. Once you find the right abstraction for it, you can start to say things about this.
Oh, thank you. Let's see if there aren't comments about that. I'll get to my next question. Sorry, give me a moment.
Thank you. I had a question for Daniel. I was wondering if you could elaborate on the difference between prediction and generation that you mentioned, and also what you think are some abstractions of how language is being generated, or the data generating abstractions.
Right. Okay, for the second one, I don't know, so that's next. For the first one, I can answer more concrete. I was referring to this work by Adam Kalai and Santosh Pampala, where somehow being able to predict the probabilities correctly is somewhat at odds with not hallucinating in some very, very, very concrete sense. Not all senses of hallucination, but these are like, one is like the error you have in prediction, the other like a error in generation.
Okay. So just Yejin, you talked about these other architectures, beyond transformers or adding to transformers. But I mean, it's the question I had was somewhat related to that, which is, do you think that it's too early to think about where do we go? What's the next architecture beyond transformers? Are we ready to start thinking about it, or is it just such a island in theory space that's where we are going to be for a long time?
There's like a bet on this, right?
I'm sorry?
There's some wager on this.
You want to put that? Okay.
Right? There's some wager, right? Like 2027 or something. Yeah, there's a website.
Oh, okay. Mm-hmm.
Sasha Rush versus
John Frankel.
Yeah.
There's some money on this.
Who's on which side?
Sasha might be the opposite, and he's working on Mamba Byte.
So he thinks we should move ahead, right? Is that the okay?
I personally, I really like all these like non-transformer directions, but yeah, would they succeed? I don't know. Like I wish Sasha wins, but it seems hard. In that, I mean, so to your question, is it too early to think about other architectures that are drastically different? I mean, it's either too early or too late, in the sense that like it works too well and everybody feels a little bit defeated by it.
Okay, so that actually brings me to the second part of the question, which is how well does it work? So, what can you point to concretely where you would say this is something completely unexpected right? So what are these capabilities that we see in LLM? So, we could, or here's another way to say it. If we were to say, LLMs are language plus search plus X, how big is X? And what are capabilities beyond what you could imagine a human doing with access to search? And they obviously have language, but let's say they have no other particular capability other than coming up with good search terms and then putting knitting answers together. So is there much more beyond that, and what can you point to concretely? I'm sorry? That's great. That's a lot. No, don't get me wrong. It's very impressive, but it's certainly not enough. That's not the sum total of human capability. So it would still tell us there's a lot more to do. So if this is what transformers and LLMs allow us to do, there's a lot of room to go further. So if this is sort of the upper bound on what we can expect, then there's a huge amount of room to explore still.
Yeah, maybe going with the same theme I was going for my talk, which is that we don't know as much as we think we do about what kind of capabilities or tasks that we can achieve or not achieve. I feel like we actually don't have a really good understanding of a task that humans do, or we don't have a good understanding about intelligence of humans. Like in the following sense, like when ChatGPT first came out, a lot of us felt like, oh, if we can do this and that, then the rest must be trivial. And then that rest seems harder than we imagined, and we don't really understand why. And then also, especially when the task becomes more like multi-step, out of distribution, and then requires some more agentic workflow and execution of like interaction with different environments or softwares, and then things become suddenly very, very hard. And I think it's in part, of course, it's hard because that kind of data doesn't really exist as online data. So in order to make that work, you need to collect more data. But people may have assumed that collecting that data must be easy, or it must be not so different from the capabilities that LLMs seem to acquire for, say, writing code. So there's something about like our lack of understanding about maybe like the notion of learnability or complexity of the task compared to what data set that we can gather or already collected versus what kind of combinatorial permutation of different situations that we need to be able to cover in the data for the model to perform really, really well for all the other compositional cases that's out of distribution. Like we don't have very firm understanding about it, and we don't know what we trivially do as a human. Like even finding this building and entering the door and then knowing where to sit, all of that, we don't know. Is it actually easy or hard for machines? And it seems that it's just a lot of open research questions to me.
I'm not going to be able to articulate nearly as well as Yejin, but so I only had three maybe sort of answers to Umesh's question. The first is, I think you started by asking what can they do that was surprising, that was impressive, and I'm like almost everything. I think that I at least this is not the progress I expected, and sure. I think that was shared even by people that understand much more than me and were that are actually working this. This is a lot of so this doesn't still say that we can do everything or most things or what we want, but like it's a bit but there's a lot of things that I think can do, in which go to, I don't know what you call language. I mean, in some sense, language is maybe everything, but like integrating sources, doing fuzzy complex searches. I mean, these are things that were not like we didn't have anything close to that before integrating common sense into that. I mean, it's working a lot and getting some progress, but this is, the how everything is integrated together, I think was, to me at least, impressive. The second thing is maybe going to what
sorry, but can I ask you a little more about that? Language already is enormously impressive. The fact that it achieves that to a great extent, or to a large extent, is an enormously impressive thing. But if once we get used to the fact, which took a lot of doing, that it did manage to do that, and now we've incorporated it. Now if we say, well, language plus search plus X, so what is X where you're impressed with X? What are the capabilities where you think it goes beyond?
Okay, so I think that, I actually want to answer a different question, which is what X can it not do? Okay. But maybe I will ask, maybe one thing to me is this exactly, which, you can say it's language, I don't know, maybe some people would say just language, but retrieval and integration, like having, asking for it for, find me, which book talks about this topic and has this, character going on, or what, it can do that very well. And I don't think there's any, this is not something that a Google search can do.
Human plus search, right? Language
even
plus
for,
search.
well, no, I don't think so. No, I don't think it's a human plus search can do it. And the second is really synthesizing things, like writing something in this, writing something in the style of something else, but also just something that now we take for granted, I think, with GPT. But if I ask it to, I think we saw some examples today, this Einstein, but also other examples, it can really write down things that, yes, they're copied, they're pasted together with phrases from different places, and but it pastes together the right phrases with in the right context to actually give me the right answer. I mean, many things I think there's, but I think more interesting to talk about what it can do, because what it can already do, it can already do. We don't need to worry about it. So I think what it can do, and I completely agree with Yejin, but I think maybe let me suggest the following. So when we approach a task, then we do a lot of exploration and fixing things on a task. Even just something simple, if I ask you to find something on the internet, then or not something on the internet, ask you for do some research on something. You start by getting some document, and then you say, oh, you searched for the wrong thing. Maybe you'll search for something else. And maybe your initial searches you're not really expecting to find it. You're just trying to figure out, feel how things look like. I know when we talk about we teach our students how to do data analysis, the first thing is look at the data, right? I mean, just see what's there before you actually start writing complex stuff. And I don't see any of these systems doing anything like that. It's doing this not just multi-step, but constantly correcting multi-step, where you're doing things because you're not because you're expecting them to work, but when you're expecting to correct it. I don't know if the third thing I want to say is maybe suggest something more concrete. Something that I feel is a challenge that people are trying to do in various ways is essentially inserting some state into the model. So RNNs were all about state, and then we went from RNNs to transformers exactly because they didn't have state, which made it much easier to train. But we went from everything with state to zero state. And there's all kinds of attempts like self notes and all kinds of other external memory, and learning the chain of learning to produce the chain of thought. All of these can be thought of as ways of inserting some limited amount of state, and I think that's something. Yeah,
the context is the state.
No, but you're not. But you're given you're not learning. Okay, so latent state, I should say. Latent state. Sorry. So latent state, right? So learning latent state, which really is what I mean in RNNs. It's all you don't if in RNN you're given the state all the time, it will be super easy to train, right? So learning latent state, I should say, and that's I think something that I think could have a lot of impact. That theoretical ideas could potentially have. How to integrate small amounts of latent state.
Sorry, latent state. You mean?
So what I mean by latent state?
Yeah.
So in something so if you have maybe I'll give it by example. So if I'm saying that the transformer can generate the right, it can't solve the answer in one step, but it can like do some chain of thought and then give the answer. But if I'm training it with a chain of thought, then it's not latent. But if I'm trying to train it so the transformer also has to figure out what is the chain of thought. So now the learning is both over the parameters and those tokens of chain of thought, that would correspond to latent state. There are other ways, or if I have some memory, if I have part of the, if I have a token, some token that I don't actually observe that represents a memory, that would be a latent state. You have a better,
I would like to add the missing X that could be super impressive as the ability to synthesize new insights, really connecting the dots and realizing what we don't know, asking really good questions, posing good questions, and also drawing conclusions that are not that trivial to draw from a lot of evidences or scientific reports. And then like how scientific papers seemingly contradict each other depending on how you read them. Some of them might have empirical settings that were less than ideal. And being able to see all of these flaws or gaps and loopholes in the existing human work, and then being able to straighten things out, and then not getting confused by conspiracy theories or non-factual facts that humans injected on the internet data, and go ahead and correct that too. All of that would be pretty amazing, but I doubt it's easily achievable. But nonetheless, I think we should work on it. We should work on it.
To anthropomorphize these systems, right? And let's say we were to teach children the same way we teach these models. What would we do? I'd give my, like when my son was 5, I'd give him a random section of the internet and say, by the way, this is the next word. Then I'd give him another random set of the section of the innocent. This is the next word. And that's all I would do. I just keep doing that to him. It might take him 20,000 years to learn, right? Which is how long it takes GPT-4 to learn if GPT-3 to learn if it learned at the same rate, read at the same rate. Yeah, it sounds terrible, right? So I think there's some sense in which like everything that we're doing is wrong at the moment, yet we somehow got lucky and it seems to work relatively well, but it has all these problems. It has a very bizarre kind of capability and fragility surface that we don't understand, right? And unfortunately, that's what we're getting if we choose to train them this way, right? So I think there's probably better ways to do it. We don't know what they are yet, but that's something we need to think about. And it'll probably, going back to the academia industry divide, I think it's good to be GPU poor because then you think, right? So that's one take, but it seems like you have some.
So sorry, just a question for you. So if we were to teach them, if we were to actually teach them, or as we were talking about in the break, think of an apprentice relationship or something like that.
Yeah,
we'd probably need a different architecture, wouldn't we?
Probably. I mean, humans are really good at learning procedures, right? In one shot, right? Like, how did I teach my son? I mean, I think I talked about it in my talk. Like, we teach our kids the algorithm for multiplication. We don't give them like a billion, 5-digit multiplication problems and hope that they generalize to 6 digits, right?
Yeah,
I teach my. They didn't learn that in school. They learned it from me.
There is the new math.
Oh yeah, I don't know the new math, but my son learns the old math from me. But anyways, but yeah, no, we teach them procedures, and then it's obvious that they length generalize, right? No, but I'm sure we can automate me for arithmetic, right? I'm sure. I mean, Khan Academy is trying to build an automated tutor. And actually, I talked to Sal Khan about how he's using GPT-4 when he incorporated into Conmigo, and it was all prompt engineering. The student asked the question, and then Sal and company insert all sorts of prompts. They say, pretend you're a helpful teacher, but don't tell them the answer. Tell them the first step, and then they give the students question, right? So prompt engineering is a failure. Prompt engineering, like some people glorify it, but it's a failure of our having engineered this weird system with a weird surface of capabilities and fragilities, right? Right now, we don't know how to solve it. That's for sure. We do. I mean, the classic example is these imperceptible adversarial examples, right? In the vision setting. I think that's a signature of our current CNNs doing something completely different from what our visual system does. And I wish we knew what our visual system does so we can imbue it into the CNNs and have them get rid of these totally weird illusions that are illusions of artificial intelligence, but not illusions of humans. Humans might have visual illusions, but they're not the illusions that AI systems have, right? Or at least, sorry, to make it more precise, the illusions that AI systems have are not our illusions, right? There's actually some interesting work showing that some illusions that humans have actually show up in AI systems, but that's a different question. That's the opposite direction.
I really don't agree with a lot of this. So two significant things I just want to, so one is, I think that comparing the amount of training data to the amount of data that a child sees during their lifetime is completely the wrong equation. But rather what you should compare it to is the amount of data that we had during evolution. Because
there's a bottleneck.
Because what's
of the length of our DNA,
that
which is not that big compared to the number of bits we need to specify every synapse in the brain.
So you're right that is a bottleneck, but nevertheless, learning even that many bits is not so trivial. Like it's not like, I don't even, that's a huge bottleneck. I mean, and so I think that's a much better calculation. And then the second thing is that a computer has the base capabilities of computer as it comes out of the box are completely different than your son as it came out of its womb, I guess. Okay? And I think that so if the base capabilities are completely different, then thinking that we should use the same methods seems to me like, why should we use the same methods? I mean, I have a machines that even my watch can process more information in a day than in a minute probably than your son can in their entire life. Why shouldn't they take advantage of that? Okay, and so I didn't do this calculation. Maybe it's not true, but you get the point, right? And so I don't think that we necessarily. It's very these analogies are very tempting, but I think we have to remember that we are thinking about teaching machines and engineering machines and not humans. And it's very insightful to learn from analogies, but why should it be the same? So I think that.
Yeah, I love this discussion. I wanted to just throw in one more thing of like, why are we trying to build models that even do the tasks that we want them to do like we do? I actually started working on adversarial examples, and now I realize why I gave up, because I felt like, why do I want the model to do something that I'm doing the way I want it to do? Maybe what we should be thinking is, what is the right use cases of these models? Like, we don't care if they can do addition. You and I can do addition, but what they can do is, like, Yejin was saying, they can process all this information and maybe find creative patterns that people missed. And those are the kind of applications we should be using, not trying to fix them to do things in a human interpretable or human inspired. Maybe human inspired is like a source of algorithms, but at least this whole human interpretability and making them correct the way we think and do these tasks, I feel like maybe it's not even the right question to ask here.
I love this discussion because it's so easy to disagree. Okay, let me first make up my mind about which I'm going to disagree with. So on one hand, I agree with you, Nati. On one hand, it started with on one hand. Wait, it's coming. That yeah, sure, machine, poor machine. That didn't go through evolution, so it should enjoy all this internet data that it can read really fast. Yeah, I'm cool with that. But like when we think about why these machines make weird mistakes that we would never make, I think it's a valid analogy to make. Like, let's compare how we tend to learn concepts from day one in a more like entirely different way compared to how machines do. And especially what I'm fascinated by the difference between humans and machine learning is that, humans have, in some sense, like agency in our learning, in that we choose what we read. It's not the case that you force me to read random page from internet. I don't think I can actually learn very well. And also, in order to learn well, I need to be able to ask questions, and then I need to be able to search questions. I need to be able to review what I want to remember, or else, I'm not going to learn very well. And in fact, I prefer certain kinds of tutorials and papers over other kinds of blog posts or other papers, because I might prefer particular kinds of descriptive writing that is more efficient way for me to acquire that knowledge. So for that reason, by the way, professors keep writing new textbooks, even though there are already textbooks, because there's something about the way that you can create new textbook that could be more efficient for human learning. And we're kind of discovering this with LLMs as well, in the sense that, 5 papers from MSR basically is an example where if they generate synthesized textbook style synthetic data, then even language models learn better. So there's something about the analogy that we could benefit from, in my opinion. And I think fundamentally, though, what seems to be, it's intellectually curious too, let alone the potential empirical gain, which is that humans are, curious being, and we know well, not all humans don't know what they don't know, but let's just say some people do know what they don't know, and they are able to reflect on that and then try to nail that down, and they do this focused learning. And I wonder whether without fixing that, just like changing neural network architecture from one thing to the other, with the state or without state, is that going to pull the magic? I doubt. I think just like the learning objective itself is kind of doomed to really unlock the full capabilities. Maybe that we need to rethink a lot of the stuff.
I agree.
Actually,
Really?
that was a good point to create agreement. Actually, I'd go one step further and say, in terms of what you were saying, Yejin, I personally feel that my learning is non-monotone, in the sense that, there are times when I feel like I know a lot, and then when more information comes in, I feel like suddenly that those insights disappeared, and it really surprises me that there's a mechanism like transformers and LLMs where you feed in all this data and something happens. Yeah. So, are there questions from the?
Thank you. On this one, I wanted to ask this question, particularly from you. Why do you think that we should get inspired by human learning when we know that we are bound to this physical world with the chemicals and the biology that is not allowing us to use silicon in our, let's say, in our body, but we have access to silicon in this world? Why? It seems really. It seems like we are putting a baseline, putting humans' intelligence as a baseline, and we want machines to follow that. While this might not be the case. And for an analogy, I want to mention movement. If you look at the nature, there's no rotational engine in the world. And if we wanted to just look at animals or our body, what moves best, we could never discover the rotational engine is the easiest thing to make for us, because we are not bound to the chemistry of the body. We are bound to, for making machines, we are bound to other things.
Actually, bacteria have rotating flagella that power them through.
Oh, I didn't know that. But to the visible eye.
Yeah. We don't have wheels.
No, I'm with you. I actually didn't mean to say that we should copy everything that humans do from all dimensions. That wouldn't make sense. I was suggesting that let's look at the difference between some differences between the way that humans acquire intelligence and the way that machines do today as a means to find some new ways of thinking about machine learning, not to copy over everything that we do. Because I'm with you in that there's no way that we're going to make a robot that can taste apples in the way that we can. I mean, what does it mean, the robot to taste the apple in the way that we can?
Can I add
Yeah.
something? What I really mean is that you said that we choose what to read because we don't have time. We cannot read as fast as the machines read. So it's not a feature of us. It's a flaw of us that you cannot read everything. If I could, I would.
And despite the fact that, arguably, some of us may have learned, in some sense better than ChatGPT. Who knows? That's up for debate. But I mean, I think there's something really interesting there that, there must be more data efficient recipe for training successful LLMs.
Yeah, there is a different answer one could give to your last question, which is if you look at learning theory, you can talk about how easy it is to learn predicates if you're just being given inputs versus being able to interact. And it can be exponentially more easy to learn if you interact. Now that's independent of machine model. So in fact, one could go a step further and say, just like we have a machine-independent theory of learning, is it possible that we could get to a machine-independent theory of intelligence? Yeah. That's a question.
I hope we can get to our first theory of intelligence.
So my question is, well, I think there is some benefit to get inspired from how humans learn to train these models, but one thing I'm curious about is what is your take, and like any of you can have, would be nice to answer it. What's your take on perhaps developing more model-based LLMs, and how do we impart these like physics theorems or whatever that we are so sure of to these large language models? To perhaps, like as Surya mentioned, like I would teach my kid how to do multiplication in a systematic way so that he or she can do, like, I don't know, 100-digit multiplication very well without needing to see billions of such examples. Yeah, how do we impart such knowledge to these models?
If you look at the like the systems that win the math Olympiad, right? They use a mixture of LLMs to make guesses, and then automated theorem provers and checkers to check it, and so forth. And with AlphaGo, right? They used a mixture of a neural network to make guesses, and then Monte Carlo tree search to improve it, right? So already the systems that are doing these more structured tasks, like poker, Go, like math and all that, they're using a combination of these things. And it's a lot like Kahneman's system 1, system 2, right? The fast and slow thinking. We have rapid, fast gut intuition. Then we have slow, deliberate, full, deductive, logical reasoning, for example. And we combine those two. And so when we're solving a math problem, we use both intuition, we make these inspired guesses, and we have no idea how we did it. But then we check them, right? And then we backtrack and all this stuff. So I think that's happening at the frontier already right now.
And also there is like physics-based, there is an entire area of like physics plus AI. So people have been like working on this, like building like climate models and using neural network for science. So I think there's already like lots of people have thought about that, and there's an yeah.
I've seen such models for like when you're designing linked gene sequences or protein design that there are simulated based things, but like they are not as impressive as these language.
I think they're quite impressive, actually.
Yeah.
I mean, I would find them quite impressive. People are able to like use physics and things you can compute for that part, but like maybe capture things like turbulence that you don't really
Yeah.
understand very well and make quadrotor robots to fly very efficiently. I think that's quite non-trivial to do, at least in my opinion.
Yeah, for example, I think this year or last year, the learning-based weather prediction has surpassed traditional numerical simulation methods. So it's also there, like we were seeing this. But I'm going to take a slightly different opinion here. I think that the way to this is with what I would in tool use, which is kind of how I would think of these things of tool use, and through the data, but not through the model. I think that what we've been seeing over and over again, and now we're seeing with transformers, there's nothing special about transformers. There's nothing like I mean, I don't completely buy the transformers capture language in any particular way. They're just a generic model, and that's easy to train, or relatively easy to train. And I think we've seen this over and over again. We want generic models that are easy to train and do not capture like anything about like what we know. And I think much of the innovation is coming from how do we, maybe this is kind of what Yejin said, that the important thing is the data. How do we train them? What training signal do we use? What kind of like maybe interactive training do we use? What, like, when I say training, I'm maybe, using that word very broadly, like learning maybe as how do we, and I think that's the way I would approach this. And I think also as a challenge maybe for this program is, I think, developing an understanding for that of moving the burden from like the model, like understanding like, what's the hypothesis class that does something. It's not the hypothesis class, but rather how in our training, in our training data, in our training procedures, and training, different training, different models of training, like, this, like even just pre-training, post-training is already a different model of training. And I think we have we're seeing many more different models of training, understanding those and how to capture things we want, like, I don't know, whether it's physics or language or whatnot, using them.
So I guess one last chance to agree or disagree with Nati. Yejin, are you?
Yeah, I guess I have to disagree.
Okay.
Should I disagree? Just for the sake of being consistent. I don't know how to
Is it working?
No, it's just gathering my thoughts. It's not easy to always disagree. I mean, but maybe, the premise of this question was that even if, whatever, AlphaGo is impressive, there's something not quite satisfactory about the way that it's done, because it feels like it's two things glued together. Whereas humans, the way that we learn multiplication rules is such that we can actually memorize the rule and then remember that as descriptive recipe to follow. And then we do follow that. We're also pretty aware that when we follow that, we can sometimes make a mistake. We're fully aware of that. And there's something like very symbolic about some of what we do with our seemingly neural brain. And that has been very fascinating to me. And similarly, sometimes we feel like, we have to create a new terminology for a phenomenon, like deep learning, We name a new thing, like generative AI, We feel like, now is the moment when we are lacking a symbol that needs to pinpoint this, concept that you and I share. And so humans have that weird capability that feels like it's just some neural signal that we have that feels significant enough to be a symbol, and then we assign a symbol to it, and then we start, seeing it as an object or concept, discrete concept almost. I found that that's quite fascinating, and I don't know whether the solution to that should necessarily be a discrete program somehow sitting in the neural network as literal discrete program, versus it's actually possible to inject that discrete program in the continuous representation of neural network. It's for me, this seems like an open research question. And then about physics world models that we know, should we or should we not inject? I have a mixed feeling in the sense that, we are able to move around without knowing necessarily all the physics laws. So there's something about it that we can do this in a very reactive manner. And then we might even create some symbolic rules about our physical behavior even. Or at least I sometimes do that to myself. Like, if I'm close to a furniture, try not to stand too close because I have a habit of kicking my leg into it, and then next thing it's like I'm like in pain. So I know some patterns, and I start generating some symbolic rules to myself, and it's a mystery to me, like that LLMs don't seem to be doing, as far as I know. I don't think they're doing it.
Great. Oh, Shafi.
So, Nati, you were saying something. I think you were saying. I'm not sure. I'm tired. It's the end of the program. but what? So you were saying that you don't think that transformers are interesting or necessarily some. No. What I'm saying is that's not necessarily that they're special. That tomorrow there'll be something else, but that what you think that is worth a study or we should study is the patterns of the data or the trainer training. And I wonder if that's because, so I'm not sure I agree with you. I don't know about transformers specifically, but I do think that the algorithm, whether it's transformers now or tomorrow will be something else, or the rules of probably are very interesting. It seems to me that I agree with you, but not because it's not that's interesting, but it's just that it's impossible to understand. But what is clear to me from this workshop, and I guess it was clear before, is that it's a useless attempt for me and some mere mortals that I understand to understand this complicated algorithm. But and therefore, why don't just give up and think about the input-output relation and what has gone into it and the data and how much less you need. But it's really because you've made this, you collective, I accuse you, you've made this beast that is impossible to take apart.
So this is, it's not so much I'd say that there's nothing special about transformers, but rather, or definitely that they're not interesting, but rather there's nothing specific to language. They're just generic. They're like I think what's special about transformers is that they're a good generic, they're like, I don't know what good means. They're a generic model for data that's like lots of different type of like, sequence or spatial or other data that comes in like, different sizes or scale invariants or whatever, that has typical patterns that we see, and that's reasonably easy to train. Okay, and reasonably easy to train, there's actually two parts of it. One is it's the steps of local search are efficient to implement. That's actually the main thing that motivated development of transformers. And the second, so that part is easy to understand. And the second is that the dynamics of local search in it are somehow, it's trainable, are well behaved, and that's something we don't completely understand, but we have some like hand wavy reasons why maybe that's the case. So that's what, especially about, this has nothing to do with like language. Now, I actually don't think transformers, when you said transformers are, they're so complicated, having chance that they're super simple. In some sense, transformers, I think their success is because they're really simple. They're combined, there's only like something like 4, I don't know, roughly types of operations going on there. 3 operations are, depending how you count, and they're combined in not a very complicated way. They're super simple. You can describe them fully in like, a few lines of either math or code or whatever you want. I mean, and actually their advantage is they're so simple, and I think you definitely can understand them. What we don't understand, and what is very complicated to understand, are the dynamics of training them. And that's really the big mystery here.
I understand the mechanics, but I don't understand how you get from input to output.
So I think that's
when I in 1980 whatever, when I went and took a programming languages course or architecture course, there was memory, there was instruction set. I knew how to go from input to output. Here there's this machine that seems to give something very unpredictable.
So do you understand circuits?
Yes.
Okay. So, but circuits also, they have like what, like, depend how you define your circuit, two maybe, or maybe one type of operation. It's super easy to understand. But if I give you now a particular circuit that has like, 3 billion gates, okay, can you look at that circuit and tell me what it does? I mean, I don't think you can, right? And I think it's the same with transformers. I mean, we understand the architecture very well in the same way to circuits. We understand why it's generic and why it's so powerful in the same way we understand why circuits are so generic and powerful. What we maybe don't understand is if you give me a particular transformer, like you just give me a bunch of weights, I can't like look at those weights and say, oh, it's doing this, and this head is doing that, and this head is doing that. In the same way, if you give me a circuit, I wouldn't be able to do that. I can maybe probe it, and we saw some. I think Jacob mostly talked about that. So that's something we maybe don't understand. But what we do understand is the potential of why it's powerful, why we can build things. The part that I think that really is the biggest mystery that we completely don't understand is, well, not completely, but like the biggest gaps is when we train these things. We train them with these local search dynamics. So if I could train a transformer just by argmin, I could completely understand what's going on to a very good level. But that's not how we train. And we know it's impossible to do that. But rather we train with just local search. And the whole, to me, the big mystery is why does local search actually, a very, maybe somewhat specific local search, maybe not so important, but how does the dynamics of local search actually find me a good transformer? You can think of circuit if you prefer. So in that part, is I think the big kind of mystery. I know. I mean that.
Oh, great. I think that brings us to the end of our time. So thank you everybody for a wonderful discussion. Thank you.